to illustrate sort of the vector nature, right? You like to do problems up here. No, you like me to do problems up here. So I'm going to do one. You hate to do problems up here. All right. So let's do one real quick here. I'm going to even put in numbers, and it's even correct. When I did it last year, I had a mistake in there in the notes, so it was wrong last year. But this year, for you guys, it's actually probably correct. I'm going to push a 2 kilogram block, but I'm not going to push straight. I'm going to push down at 45 degrees. Ooh. And it moves at 0.6 meters per second. On a surface with a kinetic friction of 0.7. Ooh, how high. Right? It's got that rough faux leather surface, you know. So the question is, what is the force? What is F push? And what is the power? So for what is F push, why don't you think about it on your own for 30 seconds. Well, I draw my little diagram, but I'm going to stand in front of it. So just go off on your own there. See, think about how you would get F push. This is moving back into the beginning of the class, right? This isn't energy part yet. This is back, Y back. How would you do it? Let's see. Let's see. Hopefully you drew something like that, right? Is that something roughly? That's not the free body diagram, but that's to get you started. So the idea was, a big part of these problems is interpreting what they mean. What I write on the board is kind of short. What we write on the exams is much longer and crystal clear, right? So if I push down at 45 degrees, it does go forward, right? There we go. Oh, I don't want to rub the Harvard symbol off of it. Oh, no. Okay. So what we would do is say if we're going to think about that force, we've got to think about all the forces. We'd do a free body diagram. All right? So we'd say we apply F push like that, right? And let's see, mg, of course, is down like that. And there must be some normal force keeping it from flying through the table like that. And there must be some friction force back. Something like that. Not drawn exactly to scale. The normal force needs to be a little longer. Okay, so then we say, what is it? Let's do some of the forces in the y. That's always the quick one. Some of the forces in the y equals 0, because it's not accelerating in the y, right? So what are the forces in the y? Oh, it's not so quick this time. We have in up. So now we're writing magnitudes, and we're putting in the signs. So the normal force magnitude is up. And mg is down. But a component of the push force is also down. Right? So we break this into components. You've got one this way and one that way. And since it's 45 degrees, they're both square root of 2 over 2. Also known as 1 over the square root of 2. So when I'm trying to write and go fast, I just call it 1 over square root of 2. It's less 2's. All right? So here we have Fp over the square root of 2 here. So that means what this is we also have pushing it down Fp over the square root of 2 equals 0. Right? So there you could say, oh, now I have Fp, except, oh, we don't know the normal force. So clearly we need another equation, and clearly that other equation is in the x. What are the sum of the forces in the x? 0, right? Because it's moving at a constant. The real problem would have said a uniform or constant 0.6. So it's moving, it's not accelerating. So it's still equal to 0. So there we have, in the forward direction, we also have a component, Fp over square root of 2, Fp over the square root of 2, right? And in the negative direction, we have the force of friction. But let's go ahead, just to speed our lives up here, let's plug in what the force of friction is. It's mu k times the normal force. The kinetic friction coefficient times the normal force here. N. All right? Those have to be equal to 0. All right, so now we have our favorite T2. We have two equations, two unknowns. So there's an unknown Fp, and there's an unknown mu k. Oh, and I'm sorry, not mu k, N. N is unknown. I gave you mu k. All right, there we go. 2 equations, 2 unknowns. I forgot the algebraic fast way to do it. It looks like, of course, I wrote everything completely different from last time. It looks like the quick thing to do that I was saying is solve this for Fp, right? And say mu k times n equals F over the square root of 2, right? So here we have mu k. I've taken this to the other side here times the normal force, but I can solve this for the normal force. It's mg plus Fp over the square root of 2, right? So there's just 2 equations, 2 unknowns. You can go to sleep and wake up later and watch the rest of the lecture, okay? So this goes over here. Mu k times n equals Fp over the square root of 2, like that. So there, we eliminated n. Thank you. And now we're going to solve for F. P, and we're going to say, okay, this is times mu k, and we take it over there, and we pull the Fp out. And what do we get? That goes over there. 1 over the square root of 2 minus mu k over the square root of 2. Oh, this is not how I did it. Mu k over the square root of 2. So that's that side. And what was left over here? Equals mu k mg. Ah, yes. So in the end, I put a square root of 2 on the top because I'm just that kind of guy. Fp equals, I took this square root of 2 and put it up there. Mu k. Oh, you always put the number in the front. Come on. Style points. Square root of 2, mu k mg. And what's left in the bottom? 1 minus mu k. 1 minus mu k. There's a completely symbolic expression. It's not very pretty. Has nothing to do with energy. This is back to, we could have given this a long time ago. This is the F equals ma chapter, the force chapter. But you have all these numbers, mu k and the mass and g, and you get 65 newtons. Let's see, how did I mess it up last year? I forgot. I think one of the square root of 2's I put in the wrong place. So we're done. No, we're not. What is the power now? This is actually the hard part, right? Now we have the force. Now we know how hard we're pushing down this way. So we can now get the power a couple ways. And they're all the same. All right, we could say, okay, he said, I believe I recall him screaming something about that. So we could say, well, let's actually do the dot product because we're really into vectors, right? Everybody's really into vectors, right? Okay. Here's how big into vectors I am. When I was gone, part of the time I was at my 25th college reunion. It will happen to you, okay? So I was sort of on vacation, and what did I do? I went to a physics class. Yeah, so I got there and I got thinking, what am I doing? This is my vacation. Why am I sitting in on this class? I'm so stupid. So I said 65 newtons, right, times the magnitude of this. It was 0.6 meters per second. Oh, you're thinking that'll never be me. Oh, it'll be you. And then the cosine of the angle between them. Right, the push is this way. And may I draw it on the free body diagram? Is that okay? It's not proper. No, I can't make myself do it. F push is this way. V is that way. I'm sorry, I almost did that. I don't want to upset anyone. So this is 45 degrees. So it's times a cosine of 45 degrees. All right, like that. All right. So 65 times 0.6 times the square root of 2 over 2 is 27.5 watts. Right, and you say, but that was easy. I want to see a hard one. Why do you always do easy ones? They're easy because I'm doing it, right? They're not easy. I make it look easy. I've laid this, I spent 2 hours laying this out where it would come out in 30 seconds, okay? That's why it looks easy when I do it. I'm not doing this off the top of my head. I screwed it up last year. That's how hard it is, okay? It was wrong, completely wrong. I'm going to send an apology to everyone that was emailed, and I don't know. Okay. So but that's literally, this is all you do, okay? You also could have said, why don't we just take the component of the Fp and multiply the component by the velocity? Yes, that's the same thing. That was the second way you could do it. You could essentially say, isn't it, you also said it was F parallel with V. Yeah, F parallel, we already did the cosine there, right? It's square root of 2 over 2. Square root of 2 over 2 equals 1 over the square root of 2. Okay? So that's really how you do these. So these power problems aren't like super tricky. Okay? If you know how fast it's going, you know what force is pushing it, that's all it is. Okay?